Page 27, characteristics of substances. So when we use the word substance, we are either referring to an individual element or an individual compound. So let's just take a look at elements. So elements, as I'm sure you're aware of, are referred to as the building blocks of matter. A group of identical atoms is referred to as an element. So an element is a group of identical atoms, and they are identical because they have the same number of protons or what is also referred to as the same atomic number. When you look on the periodic table, the ones in our chemistry reference tables, each element in its individual box, you will notice the element symbol is in the center of the box, and lower left there is this bolded number. So it's bigger than the other numbers in the boxes, and it is bolded, and that's where you will find the element's number of protons, or what is referred to as the atomic number. So you don't have to have it memorized, but just know what that piece of information represents. For us, the atoms that make up an element represent the simplest form of matter to exist naturally and independently here on Earth. We can't break an atom down into even simpler matter that will exist on its own. The elements, they are listed on the periodic table. And a lot of times I will abbreviate periodic table as PT in the notes. So elements are listed on the periodic table in the order of increasing atomic number. Now let's see if I can get this page to move up a little bit. Whoa, a little too far. Technology. I gotta learn to control this. Okay, here we go. So now, continuing on. Elements cannot be decomposed. Which means chemically we cannot break them down. So I'm going to write break down. So elements cannot be decomposed, or we cannot break them down into simpler matter. They're as simple as they get for us in our everyday lives. So element chemical formulas, the way we represent chemicals in reactions, tend to either be monoatomic or diatomic. So that prefix mono, as in number prefixes, represents the idea of one, and then we have the little word atom. So an element's chemical formula, if it is monatomic, that means that there is only one atom in the chemical formula. And that, lucky for us, is most elements. So for most elements, the PT symbol is the chemical formula. Examples, like the element gold, it's considered monatomic, so its symbol and periodic table symbol and chemical formula are simply AU. Also like the element carbon. So carbon is considered monatomic, so its periodic table symbol and its chemical formula are both represented by a capital C. But there are other elements whose periodic symbol and chemical formula are a little bit different. So elements that are not monatomic, they are referred to as diatomic. So di means two, and of course we see that little word atom present. So these particular elements, 2 atoms are required. So 2 atoms represent the chemical nature of this element. So it has to be in the chemical formula. Now, on the periodic table, there are a total of 7 elements that require their chemical formula to have a subscript of 2. So I'm just going to use X as a general symbol, and then it needs a subscript of 2. That makes it a diatomic element. So here we go. There are a total of 7 elements. You need to have these memorized, and so there are some ways that you can memorize this. So there's some different types of mnemonics. So one is known as the 7 to Heaven Club. Another one is like a crazy scientist name. So the scientist is known as Dr. Brinkelhoff, and you spell Brinkel as capital B R, capital I, capital N, capital C, lowercase l, capital H, capital O, capital F. Or his co-worker, you can also use his co-worker's name as Hofbrinkel. So capital H, capital O, capital F. So Hofbrinkel, capital B, lowercase r, capital I, capital N, capital C, L. So let's take a look. I suggest that you get out your big periodic table in your reference table. I have a little one here on the sheet, so let's take a little bit of a look at it to find our diatomics. See if I can get this to move up a little bit. Here we go. So the 7 to Heaven Club, Brinkelhoff, Hofbrinkel. So this is one of the things. On your periodic table, you should make like a little key here, and I'm going to use a purplish color, and so I'm going to put a dot. So wherever I put the dot, that for me is going to represent, hey, this is a diatomic. And if it doesn't have that purple dot, then that means it's a monatomic. So 7 to Heaven Club, there are 7 of them. So if I take a look at it, H in the Hofbrinkel stands for hydrogen. Okay? O in Hofbrinkel stands for oxygen. The F in Hofbrinkel stands for fluorine. The capital B lowercase r in Hofbrinkel stands for bromine. The capital I stands for iodine. The capital N stands for nitrogen. And then the capital C lowercase l stands for chlorine. Now, if you take a look at this and you trace 6 of them, the shape that they make is a 7. So here are your diatomics. The 7, and then H is by itself off in heaven. So the 7 to Heaven Club. Each of these elements require a subscript of 2, or their formula has to be written with that subscript of 2. Without it, then it's not its chemical formula. The other thing that we're going to talk about here with elements is the element subclassification on the periodic table. There are 2 major classifications. Elements are typically put into 2 broad categories. A is they are known to be metals, and B, nonmetals. Now, on our periodic table, there is a stair step, that bolded stair step, that gives you the rough breakdown of which side metals fall on versus nonmetals. So, as a general rule, if an element is listed or shown to the left of that stair step, we're going to refer to it as a metal. So when I'm talking about element classification, I usually just short form metals as an M. And then if they are shown to the right as a general rule, they are considered nonmetals. So I use an NM. Now here's the thing. Most of you are familiar with the general properties of metals because a great example of a metal is aluminum foil, which many of you have used. So think about aluminum foil. Well, aluminum foil, like most metals, they tend to exist in the solid phase. So most metals, all but one, are solid at room temperature, okay? When you look at aluminum foil, when you first take it out before it has been used, it is very shiny. So that means it has luster. Now, aluminum foil, you can manipulate it from that beautiful shiny sheet. You can crumple it into a ball, fold it, mold it around different things, because metals like aluminum foil, they are malleable. And a sister characteristic to being malleable is ductile, being pulled into a wire. And then the other thing, you know that many of your pots and pans at home are some sort of carbon steel, which is the main component is iron or aluminum, or they have copper in them. So we tend to use metals to conduct energy. So metals, they conduct both heat and electricity. So here's the thing. You are familiar with aluminum foil, and if you recognize these terms in reference to aluminum, then you also know these are the general properties of all of these other metals. So therefore, the other major classification on the periodic table is the nonmetals. See if I can move this up a little bit. There we go. So nonmetals, they are, non means they are not metals, therefore their properties tend to be opposite. So nonmetals, depending on which one we're talking about, nonmetals exist in all three phases. So some nonmetals are solids, some are liquid, one is a liquid, and some are gases. Since they are nonmetals, they tend to be non-conductors. And solid nonmetals, they are not shiny. They tend to be dull. You can't pick it up and fold it and manipulate it into another shape because it will crumble in your hands, so they tend to be brittle. So nonmetals tend to have the opposite properties of metals.